Hey everyone and welcome back to PrepFusion. I'm Anish and today we'll start the lecture 9 of engineering mathematics from linear algebra chapter. So today we'll study about the eigenvalues and eigenvectors. So this chapter, right, is very important. Very important. This is a 3-star chapter. So whatever I say, whatever I speak, okay, you have to listen to me very carefully. Okay, because many students eigenvalues is okay, but many students get confused with eigenvectors. So I don't want you to get confused or have any confusion, right? Eigenvectors is the same thing that we have been doing until now, but just in a different way. And the significance, practically the significance of eigenvectors are different, but whatever mathematical tools we will use, we have already learned those things. We'll just use those here to find the eigenvectors. Okay, so yeah, this is a very important chapter and maximum chances are there one question will come from this topic. Okay, from all of your branches, right? All of your branches. So in the previous lecture, what did we learn? We learned about the homogeneous equations, solution of homogeneous equations, what are the conditions, and about the LU decomposition. So what are the possibilities of solution of homogeneous equations? It can have only consistent set of solutions. Why? Because its rank of coefficient matrix will always equal to its rank of augmented matrix. Rank of A is equals to the rank of A colon B. Okay, so if it is equal, then it will always be consistent. Now either its determinant can be 0. If determinant is 0, then that means it has a free variable. That means it has infinite number of solutions, because that variable will cause it to cause the solution to change every time, right? And if the rank of the A coefficient matrix is equal to the number of unknowns, then obviously it will have unique solution, one solution only. And what will be that solution? That solution will be zero solution, because x equal to 0 gives 0 on the right hand side. That's why unique solution is all zeros, also known as trivial solutions. And non-trivial solutions means not boring, okay, not zero, hence it is known as non-trivial infinitely many solutions. So that is basically what we learned till now. So let's start with this lecture. So here we'll first learn about eigenvectors, what is eigenvector, and from there we'll learn about eigenvalues. Okay, so yeah, let's start basically slowly. Just listen to me carefully, you will understand everything. Okay, you should have your full focus here. Now, what is an eigenvector? So in definition of linear algebra, the eigenvectors of a square matrix are non-zero vectors which when multiplied by the square matrix would result in just scalar multiple of vectors. What does it mean? So basically I have a square matrix A. I have a square matrix A. Okay, now if I multiply some eigenvector, some non-zero vector. Now what is a vector? For now, just understand that vector is a column matrix. Just keep this in your mind that vector is a column matrix. We'll learn more about vectors in next few lectures after learning this. Okay, I don't want to break your concentration because this is very important topic. That's why for now just you try to understand vector is a column matrix. Slowly also I will give you more definition about vector. For now just understand that. So let us say I have a vector V. Okay, V matrix, which is a column matrix, right? So if for us to this for this matrix multiplication to be valid, what needs to happen here? If the order is n cross n of this A matrix, n cross n, then its order should be n cross 1. Column matrix it is, so number of rows is more, obviously number of columns will be 1 only, so its order is n cross 1. Now its order is n cross 1, that means our answer will be something like in terms of n cross 1 only, because I will only take the outer orders, right? Now what is this statement telling us? It is telling us the eigenvectors of a square matrix. So eigenvector, this is the eigenvector of this square matrix, are non-zero vectors. This is non-zero. This is a non-zero vector. Remember this, okay? Which when multiplied by the square matrix, if I multiply its own eigenvector by its square matrix, by the same square matrix, would result in just the scalar multiple of the vector. So if I multiply, I will get a scalar multiple of the vector itself. Okay, so it is just scaling it, it is not transforming it. Okay, so yeah, and it is also not equal to 0. This point is very important. Eigenvector is defined as it is not equal to 0. Eigenvector cannot be 0. So if it is 0, it is always satisfying. It's always satisfying. So it doesn't make any sense. That's why this is basically a definition. Okay, short definition. So here they have also written a vector V is said to be an eigenvector of a square matrix A if and only if AV equals to lambda V. So if I multiply the eigenvector with the same square matrix, I will get back the eigenvector itself with a scalar multiple of lambda. So this is basically the definition of eigenvector. Nothing fancy to be nothing fancy here, but these are very useful things. Why these are useful? These are also used in many applications. I will tell about the applications, and that's why we are so much concerned with this. We are so much concerned with this eigenvectors. Okay, so now the word eigen means own, characteristics, or proper or typical. Eigen means own or own, so it's eigen means own. So this v is the v and okay wait, and it is originated from German language. Thus eigenvectors of a matrix are also known as characteristics vectors of the matrix. So it is all like in eigen also means characteristics. Okay, so that's why it is known as the characteristics vector of the matrix. Why? Because it has some information of this matrix. Because if I multiply v with this eigenvector, like if I multiply the eigenvector of a with the a itself, I am getting a v again. So it has some information about the matrix. That's why it is very special. It is very special, and we are really concerned about this. Okay, so yeah, let me tell you like a bit about vector. So vector in physics, what we know, this is about the physics definition, right? Physics definition. So this is the physics definition. So if this is a physics definition, that means we know that I cap, j cap, we remember, right? So I have 3 I cap and j cap. So I cap means in the x direction, unit vector in the x direction. So 3 I cap, 1, 2, 3, and 1, 2, 3, 4. Okay, 1, 2, 3, 4. So yeah, this is the case. So now what will happen? What is the vector? Vector is the point here, and I have to make a line from here and arrow showing this direction, right? Arrow is showing this direction. So arrow is showing this direction. This is 3 I cap plus 4 j cap. Okay, 3 I cap plus 4 j cap. Now like this is a vector, right? This is a vector in physics. So this is how we represent this diagrammatically, diagrammatically, right? So now if I want to represent in the matrix format, how do I represent it? So I can represent it like this. Okay, v vector is equal to 3, 4. Okay, and here the first row is I for the I component, and the second row is for the j component. We represent it in terms of column matrix. So for now you just understand this, that we are representing it in terms of column matrix, the vector. Okay, there is a column matrix. So our vector in physics becomes a column matrix here, because in computers, right, in computers you can't simply put 3i 4j. You have to put in the matrix format, in the array format. So that is how we put, right? So now let's say like what does scaling mean? Here it is telling, right, which when multiplied by the square matrix would result just the scalar multiple of the vector. What does scalar multiple of vector means? Scalar multiple of vector means simply this is becoming, if I do scalar multiple of this will become 9, 12, and in actual diagrammatically or visually this will become 9i plus 12j, right? So 9i plus 12, basically what will happen, this will just, I will just delete this. Okay, no, not this. If I draw it, it will be just scaled version, which is 9i plus 12j. Okay, now if I want to do multiply -1, this will be in the behind, okay, opposite direction. Direction will not change. Okay, just it can be either, direction can be either opposite or exactly same. It can, direction cannot go to any other angle, right? Any other angle. Okay, so here that is what we mean by scaling. So here scaling means, I will just take scaling. It means direction can either be same or exactly opposite. Exactly opposite. Direction can either be same or exactly opposite. Okay, so it can't be any other direction. So this is what we mean by scaling. Basically scaling a vector. Okay, so what are the key points? So a row matrix and a column matrix is also known as vectors with reference to matrix. For us, right, for now, just understand that vector can be called a row matrix or a column matrix. So this, right, this can be represented like this also. This can be represented like a row matrix 3 4. Okay, so either way, okay, but we generally prefer this column format. So we prefer to represent our vectors in column matrix. That is why we use this. That is a general convention. So yeah, either way, this is like a row matrix, but here it is transpose. So this is equal to this, because generally we don't want to waste 3 lines. We just want to write everything in 1 line, because in computers, right, writing 3 lines is difficult in 3 lines. I hope you have done some assignment in words. So if like here this is 0, then I have to put all the space over here, then write 3. Okay, that's why we don't want to do that. We write this in the simple one row, right, to easily type everything. That's why we write this in the transpose format. So this is same as this, but this is easier to write in the computer. So that's why you may see in the questions it is written like this. Okay, that is the reason, basically, no other reason. Okay, so let's do a few examples. Now we know what are vectors, right? We know what are vectors. Vectors are either column matrix or row matrix, that we know. Now here like you have to tell me the dependence and independence of the vectors. So if the x are equal to this, then you have to tell me about dependence and independence of the vectors. Okay, have we done this before? Have we done something like this before? So if we go back to our previous lectures, if we just see just here, the last question, I believe, here, oh no, not the last question, this is the LU decomposition. Before this question, no, not this one also. Okay, yeah, this one, I think. Yeah, this one. So if you remember, I told you something, right? I explained a very important thing here. Two linearly independent solutions. Where solution was a column matrix. So that was also a vector. I didn't say anything about that because that didn't came up. But whatever solution we got, right? Our x matrix, this x matrix, this is a vector. Here also, this is a vector. Now, how can we understand these two are linearly dependent or independent? If these two are linearly dependent, that means one will be the scalar multiple of the other one. So yes, one column is the scalar multiple of other one, or one is the, if there are only two, it will be scalar multiple. If there are two or more, then it will be linearly dependent on the other one, linear combination of the other two, okay, or other three. So if you have 3, then we can say one column matrix will be the linear combination of the other 2, or more than that. How many number of column matrices are there? Column matrices. Okay, so that is what we mean by linearly dependent matrix. So it is linearly dependent. So first case we saw it is a simple scalar multiple, it is linearly dependent. Next case we saw that we are finding our vectors. These are 2 vectors, right? These are 2 vectors, and these 2 vectors are linearly independent, because if I multiply, okay, the first element is same, okay, then second element is 1 0. So if I have to multiply 0 with this, if I multiply 0 with this, other elements will become not equal. So obviously these two are not equal, then with this one linearly not dependent, hence they are linearly independent. These 2 vectors are linearly independent. So we have already done this. This is nothing new. We are already doing vectors. Just I didn't say you that this is a column matrix, but I didn't say you that this is a vector. Okay, that is important. So that is how we understand whether this is a linearly independent or dependent vector. Okay, so this was one way to find that one, right? Like number of dependent columns, the column matrix are dependent. So that is how you find dependency. Now there is also another way. How there is another way? So basically what you can do, so you haven't given this set of vectors, right? You haven't given this set of vectors. How to check the linear dependence? What you can do, you have to just check whether one column is dependent on the other. What you can do, you can directly write this in the matrix format. All the columns 0 1 2 1 2 minus 1 1 0 1, okay, 1 0 1 0 1 2 1 2 minus 1 1 0 1. Okay, so yeah, this is basically in the matrix format. Now these 3 are the columns, right? These 2 are the columns. So what was the condition for dependence or independence? Basically, if they are dependent, then I can write this C1 in terms of C2 and C3, okay, in some scalar multiple of C1 and C3, right? So for that, what criteria we used, how we checked whether the columns are dependent or independent, or the rows are independent or dependent, we check by rank. So we have to check by rank. So if you want to check by rank, check rank. So basically what you can do, first you can calculate the determinant of the highest minor, or you can convert it into row echelon format, and from there also you can understand whether you are getting a row of zeros or not. So what I'll do, I'll try to find the determinant. So if I try to find the determinant, what I can do is I can simply subtract this, right? Or I don't need to even subtract. I can simply break this down in terms of the first row. So this is 0 times 2 times 1, and this is 0 also, because basically this is 0 only because 0 times something, and determinant of a I am calculating, and this is minus 1 times 1 minus 0, and this is plus 1 times minus 1 minus 4. Okay, so this is minus 1, this is minus 5, this is minus 6, which is not equals to 0, which is not equals to 0. So our determinant is not equal to 0. That means our rank of A will obviously be 3. It is a full rank matrix. Full rank matrix. Okay, that means 3 linearly independent columns or rows, right? So we have 3 linearly independent columns. So obviously these 3 vectors are linearly independent. So what can I say? How do we see? So now we have come to the terminology part, because basically in the examination the options will be something like this, that our x, right, x is a set of x1, x2, x3. So here this is a set, right, set of 3 vectors. I hope you understand set. Set is a collection of multiple things, like things, right? So this is a set of 3 vectors. Now I can say that x, which is a set of x1, x2 and x3, form a set of linearly independent vectors. Form a set of so yeah, so this is the case, right? This is the case. So now basically let's do it for the next option. So this is the first one, so let's do it for next case. So if I do it for the second case, so again, right, I will repeat the same process. I will just convert this into a matrix format because it is easier for me to understand like that way. Okay, else like we already know how to find the linear dependence. Okay, so let me convert this. So let's name it as a1, this, let's name this as a2. So this is 0 1 2 1 2 minus 1, and this is 0 0 0 0 0 0 0 0. So basically this is all zeros, right? This is all 0. That means my rank will be obviously less than 3, which is in this case I think rank is 2, because let's take this 2 cross 2 minor. So this is 0 times 2 minus 1. So like 2 cross 2 minor, okay, is non-zero. So m2 cross 2 is not equal to 0. m2 cross 2 is not equal to 0. So if m2 cross 2 is not equal to 0, so basically rank is what? Rank is 2, right? So basically we have one dependent, we have one dependent, basically we have one dependent dependent column. So one dependent column, right? So basically the vectors are set of linearly dependent vectors. So why? Because if I simply multiply 0 with this, right, I get back this vector, right? That's why. So I can say x equals to x1, x2, x3 are set of linearly I should write this in short format, LD, right? Linearly dependent vectors. Okay, just we're learning about dependence and independence. Basically, these are also important. We haven't even started about eigenvectors yet. Okay, just we're taking baby steps now. So yeah, don't like think that these are all easy. These are not easy. Okay, so if you understand this very well, the foundation is very well, then you will understand eigenvectors much better. So let's understand one more concept. This is the last concept, that is the set of mutually orthogonal vectors. So if x equals to set of two vectors x1, x2 is a set of orthogonal vectors if x transpose dot x2 is a null matrix, or x1 transpose dot x1 is a is not a null matrix, and x2 transpose x2 is also not a null matrix. So basically this multiplication, right, some x transpose x is also known as the inner product, right, inner product. So x transpose is also known as the inner product. So basically this is inner product. Now inner product also has two categories. This is the dissimilar inner product, dissimilar inner product, and this is a similar product, right? Okay, I have forgotten the spelling of dissimilar. Just hold on a second, let me check if I am correct or not. Dissimilar, right? Sometimes I forget the I'm correct. I'm correct only. Okay, I was thinking what I was doing wrong. Okay, I just put double L over there, so that was wrong. Okay, I just put double L over there. This was single L. So and this is also similar because here both of them are same matrix. Just I am taking the transpose and multiplying. Similar. Okay, so basically if the dot product, this is also like you can see, right, this is like a dot product itself. So I just put in a dot over here to signify that thing, that this is like a dot product, right? So let's say if I have a vector I plus j and if I have a vector I minus j, are they orthogonal? So if you want to plot a graph, right, I plus j will be somewhere around here, I minus j will be somewhere around here, so they are orthogonal. So that is basically what it is saying. Orthogonal means 90 degree to each other. That is why, right? So if you have a vector I over here, j over here, so they are orthogonal, right? So yeah, that is what this is doing. This is doing the dot also known as dot operator. This is doing the dot product, and obviously dot product with itself will be 0 because there is no angle, right? Sorry, dot product with itself will be 1. Dot product with itself, I dot I is 1, j dot j is 1. That's why it should be non-zero and it should be 0. Then only the dissimilar product should be 0. Then only they are orthogonal to each other. Okay, so let's do this. Understand the definition. So definition, S is a set of x1 x2 all the vectors, individual column all the vectors, set of mutually orthogonal vectors if they satisfy the following condition, that the inner product, dissimilar inner product should be equal to 0. It is a null matrix. Basically I should write a null matrix. And this is also a null matrix. Okay, basically the dissimilar product is n cross n and the similar product is n cross n. This is also a null matrix and this is not equal to 0. This is not a null matrix. The similar product is not a null matrix and the dissimilar product is a null matrix, and it is a set of orthonormal. So I should write here orthonormal. Okay, now what do you know orthonormal? Previously also we have studied about orthonormal matrix, right? So basically orthonormal means basically this, right? The dissimilar product will become 1. Why is it? Because the magnitudes of each vectors is 1. That's why basically you say I and j are orthonormal because the individual vector has magnitude 1 and they are orthogonal to each other. Okay, that's why. So here also the similar product, right, is 1. Okay, you can understand I dot I 1. Now I the I plus I dot I plus I, what is it? I plus I dot I plus I is 1 plus 1 because I dot I is 1, I dot j is 0, j dot I is 0, then j dot j is 1. So it is 2. So we are getting 2 over there. So it is not 1. And anyways, you can see the magnitude are not 1. Magnitude of I plus j is under root 2. Magnitude of I minus j is under root 2. Okay. So from there also you can understand. They are not orthonormal, they are orthogonal. So basically, I already the example that I was going to take, I've already explained to you. But yeah, let's do this. Basically, they are saying for the given set of vectors, check if it is set of mutually orthogonal vectors. So here we have been given set of vectors, right? So how you can check? So if you don't want to go to the physics route, if you don't want to visualize it, you can simply use the formula what you know. What you have to do, you can relate like that, right? You have to do the dot product. So if you have to do the dot product here means the inner product, which is x1 transpose dot x2, dissimilar inner product. Okay, first I will do dissimilar inner product between the two vectors. So the first one is 1 comma 0 transpose 1 comma 0 transpose is our x1, and I am taking the transpose again, so it will become 1 comma 0 itself. Transpose or transpose is the same vector, so same matrix. And then I am taking x2 is what? 0 1 transpose, so it will become a column vector 0 1. Okay, and this is equals to 1 times 0 is 0, 0 times 1 is 0, so this is 0. Okay, then next is basically this vector, right? This vector. So sorry, not this. Next we have to do a similar product also. That should also not be 0. If that is 0, then it will be difficult. So basically this is x1 transpose, sorry, not 2 actually. x1 equals to what? This is 1 comma 0, and this is basically I will take the transpose of it. Taking the transpose of it. So this will be 1 comma 0. So this is 1, and x2 transpose dot x2 0 1. Okay, no, 0 1 and 0 1. So this is also 1. Okay, so now let's go to this 2 thing. Let's go to this 2. So the next thing is that this is basically this is satisfying the case of orthonormal, not orthogonal. Orthonormal vectors. Okay, so it is a set of orthonormal vectors. Or what you could have understood is that this, right? This is simply I, and this is simply j. I, j. Okay, and yeah, that is basically you solve this. Now let's do the second case. Ij and ij obviously are orthogonal and orthonormal because their magnitudes are 1. Now let's go to the second question. So the second one is 1 1 and 1 minus 1, right? Or minus 1 1. Now it's a bit different, 1 1 or minus 1, so that's why it's a bit different. So I will do the dissimilar inner product first. So this is 1 1 and this is minus 1 1. So this is, okay, what happened? Minus 1 1. So this is minus 1 plus 1 minus 1 plus 1, which is equals to 0. Okay, now next is x1 transpose dot x1. x1 transpose dot x1. x1 transpose dot x1 is, this is basically 1 1 and this is also 1 1, right? So this will be 2. So this is not equal to 0, but this is also not equals to 1. So next is x2 transpose x2. So this is minus 1 1 and this is minus 1 1. So this is 1 plus 1, which is equals to 2. Just hold on a second. Yeah, sorry for the interruption. So basically, as we can observe here, this is a set of orthogonal vectors. So this is a set of x x1 x2 is a set of orthogonal vectors. Okay, so I should write this for the previous one also, not like this. I should do this in a more formal manner. This is orthonormal, right? Okay, so this is basically about the orthogonal and orthonormal vectors. Now let's restart our eigenvectors and eigenvalues thing. So let's now understand what is eigenvalues. So we have learned about eigenvectors. Okay, eigenvector is basically a scaling vector, basically not scaling, basically eigenvector of a matrix is a column matrix or a vector. If I multiply that vector with its like matrix, right, with the A matrix, then I get the same vector itself with a scaling factor. That factor can be 1 also. Okay, that factor can be 1 also. I can get the same vector back also. Okay, and that scaling factor is known as the eigenvalues. So eigenvalues of a matrix are scalars by which some vectors, eigenvectors, change when the matrix transformation, or basically the same A matrix multiplication, is applied to it. Here the multiplication, they are talking about the transformation. Basically visually, right? Visually it is lying on the same plane, same line, because I'm just scaling it. That's why it is talking about the transformation. Whatever transformation we are applying, it is lying on the same line, either in the opposite direction or the same direction. It is lying on the same line or same plane, whatever. In 3D in same plane you can say, sorry, in 2D, yeah, 3D in same plane you can say. Okay, so that's why it is called as transformation. No need to think much about that. Now let's read back the definitions. In other words, if A is a square matrix of order n cross 1 and V is a non-zero column matrix, so it has to be non-zero, very important, of order n cross 1, such that AV is lambda V, then the lambda is basically the eigenvalues. Then the scalar real number, it is a real number, basically eigenvalues are real number here. Okay, lambda is called an eigenvalue of the matrix A that corresponds to eigenvectors. Okay, it can be complex also. Eigenvalues can be complex also. Okay, doesn't mean that it has to be real only, it can be complex also. Okay, called an eigenvalue of the matrix A that corresponds to eigenvector V. So for a particular eigenvector, that will be the eigenvalues. Okay, so for that particular eigenvector, that will be the eigenvalue. Now for a different eigenvector, some eigenvalue will be different. What do you mean by that? So A can have at max 3 eigenvectors. Why? I will explain it to you later on. But for now, understand that A can have maximum 3 eigenvectors, because not 3. A can have maximum of n eigenvectors, whatever is the order of this A. Right? Now if A has this eigenvector, so if I multiply one eigenvector, I am getting some transformation with some scaling factor. Okay, let's say 2. Now I have another eigenvector. Okay, that is on some different plane. So this is, let's say this is one vector, right? This is one vector. This is one vector. Okay, now if I have another vector if I have, now if I do the transformation, I'm getting some scaling factor, but luckily the scaling factor is same as this. Here what is the scaling factor? It is 3, right? Scaling factor is 3. Here also scaling factor is 3. So eigenvalues can be same for distinct, different, independent eigenvectors. Eigenvalues can be same. I'm just showing you visually. Here I have 2 different eigenvectors, and if I multiply with the A matrix itself, I'm getting scale value of the eigenvector, and they are same, they are not different. Okay, so basically they can have same eigenvalues, that doesn't matter, it is just simply a scaling factor. Okay, it is simply a scaling factor. But if I have this eigenvector, right, if I have this eigenvector, then I can have only this for this eigenvector particular I will have only one eigenvalue. Okay, for this eigenvector I can have only one eigenvalue. I cannot have multiple eigenvalues, because for one eigenvector if you multiply, then I will get obviously one scaling factor, right? I can't get multiple scaling factors. That is very important point. We'll obviously go through those points later on. I'll just giving you a brief intuition of what we are expecting in the next few slides. So yeah, this is about the case. Like, what do we mean by eigenvalue that corresponds to eigenvector? For that particular eigenvector, we get that particular eigenvalue. Okay, so what are the applications of eigenvalues? So applications, first, eigenvalues are used in electrical circuits. We have already learned in state space solutions. Okay, where I have already used, you can watch there the eigenvectors chapter. There also I have tried to explain visually, not mathematically, visually, what does eigenvalues mean. Eigenvalues is used in electrical circuits, quantum mechanics, control theory, everywhere, right? Everywhere it is used. Like in electrical circuits, you can see that it can be converted into like your normal state space representation, right? That's why we use in electrical circuits. So next is they are used in geometric transformation. So we can geometrically transform, right? As you can see, it is still lying in the same plane. We can do multiple geometrical transformations with the help of eigenvector values. And obviously there are more like applications of this which you will not understand. That's why I'm not talking about it. So let's take one example. So let's say this is the most simplest example, that let's say I have some matrix A which is 3 0 0 3. If I have some matrix A 3 0 0 3, okay, now can you say what will be its eigenvector? Can you say what will be its eigenvector? So its eigenvector can be anything. Its eigenvector can be anything, right? It can be anything. How? So because this is like an identity matrix, this is 3i, right? And whatever I multiply with 3i times any v, right, will be 3v. Okay, so basically this is getting scaled with 3, so this is always satisfying. I multiply any eigenvector, this will always satisfy. Okay, always satisfy. But my eigenvalue will be one single eigenvalue. Okay, only one single eigenvalue, that is 3 in this case. So not 3, sorry, my eigenvalue will be only 1, because this is 3. This is 3i, right? This is a or itself, and I'm multiplying. Sorry, my eigenvalue will be 3 only. This time. So basically, what do you mean by this? So you can take an example, right? Let's say I'm taking now I will write eigenvector as x. Okay, you can write x, v, whatever, it doesn't matter. It is just a basic notation. I'm taking it as 3, 4. So if I take my eigenvector as 3, 4, now if I multiply ax, what do I get? This is a 3 0 0 3, and x is 3 4. Okay, so x is 3 4, so this becomes basically I multiply 3 with this, becomes 9, and this becomes 12, right? So if I take 3 common, this will be simply 3, 12. So here what do you see? This is scaled by 3, right? This vector is scaled by 3. So eigenvector is 3. Okay, and basically this is known as the eigenvalue, and this is known as the eigenvector, because I am getting the same vector back again. But in this case, this is a exception basically. Why? Because for the identity matrix, right? For identity matrix all identity matrix of order n cross n, all column matrix of order n cross 1 will be eigenvalues. Okay, so this is basically the case. Okay, so let's now do one question. This is also another example, and from here also we'll understand this better. So basically how to find the eigenvectors and eigenvalues. So you have to find the eigenvalues and eigenvectors of the following matrix. So how do you find it? So basically I have given this matrix, right? So this equation, this matrix has to satisfy the following equation: A times this V should be equals to lambda times, or I can write X, because next we will only see X, and X is very important, right? So A times X is lambda times X. Okay, so this is the main equation, right? Of this is the definition of our eigenvectors. This is the definition of eigenvectors. So can we do something? Can we interchange something? Yes, we can. So what we can do is, I can take to this side, and here, right, I already know my X is not a null matrix. Okay, X is not a null matrix. X is not a null matrix. Okay, now if X is not a null matrix, I can take this to the left hand side. Ax minus lambda X equals to 0. Okay, this is what we can do. Now what I can do, I can take the X as common. Okay, right, this is A minus, now if I take the common, right, this is in n cross n format, and this is also, I take X common, so here I have 1 left. What does 1 represent in matrix? It represents identity matrix. So 1 is normal element number, and 1 in matrix format represents identity. So In, right, this is n cross n In. Okay, and obviously we have a X multiplied. I have taken the X common, which is over here, which is equals to 0. Which is equals to 0, right? Now is this something familiar to us? You might say, sir, no, this is nothing familiar. I haven't seen like something like this. But if I say you have, so you have seen something like this, right? You have seen something like this: A times X equals to 0. Okay, you have seen this. What is this? This is homogeneous equations, set of homogeneous equations, right? Homogeneous equation, and the solution is the solution of homogeneous equation. Homogeneous equation. Now if I change this, if I write E, okay, this is the standard notation, equals to A minus lambda In, right? Just change this notation, lambda In, and if I change this to E times X equals to 0. This is a null matrix, right? On the right hand side, this is a null matrix, null. Okay, so this is also a homogeneous equation, right? This is also a homogeneous equation. Okay, now it doesn't matter, right, whether here E or A, anything, M, N, this is a number and this is a matrix. So this is a solution of this coefficient equation, like homogeneous equation. So what are the possible solutions here? I just revised you at the starting of the lecture. The possible solution can be either infinite or 0 solution. But X is not equal to 0. X is not equal to 0. I have already established that our eigenvector cannot be equal to 0. Why I am talking about eigenvector? Because whatever the solution I get, right, whatever the solution I got from here, it was a solution for X. And what is X? X is eigenvector. X is eigenvector. So X is eigenvector basically. So here I should write X is eigenvector. I should write here. Lambda is eigenvalue. X is eigenvector and lambda is eigenvalue. Okay, so here basically, what is this X? The solution. What is the solution? Solution is this X, right? Okay, solution is this X, and X is eigenvector. So if I am able to find the solution, then I am able to find my eigenvector. So my next target is finding the solution of homogeneous equation. So find the solution of homogeneous equation. How to find the solution of homogeneous equation? Basically, there are two possibilities, right? One is the trivial solution, that is x0, which is obviously I rejected that because my eigenvector are not 0. What is the next thing? Next thing is infinite solution. For infinite solution to happen, what needs to happen? The determinant of this matrix needs to go to 0. Rank has to be lesser than the number of unknowns. So for infinite solutions. My determinant has to go to 0. I may write this, right? E, determinant of E goes to 0, which is equals to determinant of E minus lambda I has to be equals to 0 for infinite solutions. Okay, so this is the first thing. So basically I hope you got the point. We have already been doing this. We have already been doing this, right? We have already been finding the infinite solution of homogeneous equations. Just in this case, the solution that we get is the eigenvector. Solution vector that we get is the eigenvector. So the let me okay, the solution vector that we get is the eigenvector. So yeah, this is the thing basically. So to find that, okay. So here, how do you now? Let's proceed. Whatever we are solving, right? So we are proceeding here, right? So our now we just put the values, right? A is 2 0 1 3. So I have to make the determinant of a comma 0. So determinant of this matrix 2 0 1 3, and I is simply okay, lambda I 2 0 1 3, and this is lambda times I. So basically lambda 0 I am multiplying the scalar, right? 0 lambda, it should be equal to 0. So from here I'll find my eigenvalues. So obviously we started with eigenvectors, but first I will find the eigenvalues, then I will put those eigenvalues in the equation, in the first equation, and I will be able to find my eigenvectors. So this is how we go around the loop. Okay, in the world also goes around the loop. So this will be 2 minus lambda 0 1 3 minus lambda equals to 0. Now if this is equals to 0, that means 2 minus lambda into 3 minus lambda equals to 0. So here lambda is equals to 2 or 3. So we have two eigenvalues we have. Also, like, you can further break this down, okay, and this is very important. This will be lambda square minus 3 lambda minus 2 lambda, which is minus 5 lambda, and plus 6 equals to 0. Okay, so this is known as the characteristics equation. This equation is known as the characteristic equation. I will already say this, but here also I can explain you this bit. Characteristics equation. Let me take this. Okay, let me take this to the next page, right? Next page. Characteristic equation. And if you notice one thing, this is a shortcut. Basically this minus 5, right? This signifies something. This signifies the trace of the matrix. Not minus 5, only 5. Okay, not minus 5, only 5. Trace of matrix. And this signifies determinant. This is basically matrix A. If you observe this carefully, right? What is the trace of A from here? What is the trace of A? 5. So it was 5 over there. What is the determinant? 6. So it is 6 over here. Okay, this is a shortcut of true cos true matrix for writing the characteristic equation of that matrix. So here I have eigenvalues, and here I have two distinct eigenvalues. What does this signify? We will also understand this later. These are two different eigenvalues. Two distinct eigenvalues. So if I have two distinct eigenvalues, it is for sure my eigenvectors will be independent of each other. Okay, for distinct eigenvalues. Okay. Now let us find the eigenvectors. How to find the eigenvectors? So first step is finding the eigenvalues, and then from there we'll find the eigenvectors. Okay, if the matrix is given, A matrix is given, basically what do? You put lambda 1 on the equation 1. Put lambda 1 on equation 1. So if we put lambda 1 on equation 1, this will become basically A times this x, right? Just hold on a second. Lambda 1 times x. So I can write my x like this. So this is 2013. This is x1, x2. Lambda 1 is 2 itself. So lambda 1 is 2 in our case, and this is x1, x2. Okay, so this will be 2x1 plus 0, which is equals to, like, I'm equating the first row. You can do it like this. There is also another method. I will also show you the other method. So I'm equating the first row. 2 times x1 times 0 times x2 is 2x1. I will just write this more precisely, plus 0. First one I will write more precisely for you guys, equals to what? The first row. First row is, here it is 2 times x1 itself. So this is 2 times x1. So here it is talking about x1 equals to x1. So this is always true, always true, always true, right? So if this is always true, I can take x1 as any free variable. I will take alpha 1. So next is this x1 plus 3x2. x1 plus 3x2, which is equals to 2x2. Now x1 is alpha 1. So this becomes x2. I take 2x2 on that side. x2 equals to alpha 1. So x1 and x2 are both alpha 1, right? Sorry, not alpha 1. This is minus alpha 1, right? Minus alpha 1. So for this, right? For this, my solution will be, for lambda equals to 1, x, the solution vector will be equals to so this is, this is alpha 1 and minus alpha 1. Now if I take the alpha 1 as common, this is alpha 1 I take common, and this is 1 minus 1. Okay, so I have infinite number of solution, and which is true also, because we need to have infinite number of solutions, right? We already explained this from the starting itself, because the case for which we are solving here for infinite solution, because a homogeneous equation can have only trivial solution or non-trivial. Trivial means zero solution, which we have already abandoned that. Okay, excluded that part. Infinite means this determinant has to 0, go to 0, and we have already done the assumption. So that's why we are getting infinite number of solution. Like we have a free variable, because nullity won't be 0 anymore. There will be some nullity, and due to that we have some free variable, and due to that I'm getting infinite number of solutions, because alpha 1 I can pick anything except 0. Alpha 1 I can pick anything except 0. Alpha 1 is not equal to 0. Now let's solve for the second one. I will just copy and paste this. This time my lambda is 3. So my lambda is 3. This is 2. This is 2. This is 3. So this is 3. So this will become 3. So if this becomes 3, then 2x1 has to be equals to 3x x1. So what you can do? Let me delete this. So 2x1 equals to 3x. 2x1 equals to 3x1. You can cancel this around, and it will become 2 equals to 3. And you might say, sir, what happened? So basically, never do this. Never do this. Okay. Whenever you get something like this, right, 2 equals to 3 or 1 equals to minus 2. So that means you must have done some blunder mistake. What mistake have you done ever? Here we can't simply cancel x1 on both sides. Why? Because x1, if we are cancelling x1 assuming that x1 can't be equal to 0, then only we can divide both sides by x1. Else we can't divide by both sides by x1 because we can't divide by 0. Okay, that's why what we should do is take this 2x1 on the right hand side. So 3x1 minus 2x1 0 equals to 0. So my x1 equals to 0. Okay, so my x1 will be equal to simply 0, right? So x1 will be simply equals to 0. Now basically x1 is 0, that is fine. X1 is 0. Now let's solve for the x2. So x1, I'm solving for the second row, 3x2, basically this 1 times x1 and 3 times x2, and then equals to this 3 times x2. Okay, sorry, 3 times x2. So obviously we know that our x1 is 0, that is gone. So here what is this equation telling us? This equation is telling us 3x2 equals to 3x2. If 3x2 equals to 3x2, that means we have what? Always true. Always true. So if this is always true, I can take x2 as anything, right? I will assume x2 as alpha 2. So basically my solution vector will again become something different. It will be zero comma alpha 2, and alpha 2 obviously can't be equal to 0. 0 comma alpha 2, so I can take the alpha 2 as common because 0 times alpha 2 is 0 itself. 0 1. Okay, so here also we are saying that we are getting infinite number of solutions. Okay, we are getting infinite number of solutions. Now any other way we can solve this? Yes, we can solve this. We can also use, like, I hope you got this point. We are getting infinite number of solutions, okay, and all these things, and only one free variable we have. All those things I hope like we will understand this a bit later on. Okay, that why we are only getting one free variable in this case. Here also we are only getting one free variable. I will tell you the second method in the after doing a bit of more theory part, right? I will say till the second method, but I will just save the steps for now. I'm just very hungry right now, so I will just pause this video. I will eat something and then I will explain the steps, formally the steps. I've just given you an example how to solve. Now we will formally study the steps, how to find eigenvectors and eigenvalues of a particular matrix. So yeah, I had good food. So as they say, right, if you don't have food in your belly, then your mind won't work. So it was like that only. So let's go back to the steps. So now we have solved this question. We have found the eigenvectors. How to find the eigenvectors I have showed you with example. Now what are the steps we need to follow? So basically steps to compute eigenvalues and eigenvectors. So first, the definition of eigenvector is this, right? If you multiply a with its eigenvector, then I will get back a scaled version of the eigenvector itself. Then here, what is n? N is the number of unknowns here. N is the number of unknowns over here, right? This order of this a. Okay, you can say. Now first step 1 is find the eigenvalues by making determinant of a minus lambda I 0. How this we got? We already understood that. This is a condition for infinite solution of homogeneous equations. So we make determinant of a minus lambda I equals to 0. We also assume that we are not getting a trivial solution. That is, my eigenvector is not null, is not 0. So here, right, after doing this, we'll get n values of lambda. So there will be n eigenvalues. So there will be n eigenvalues. N eigenvalues, that is lambda 1, lambda 2, dot, lambda n. Okay, there will be n eigenvalues. Okay, next step 2. Next step 2 is we have to put the eigenvalues in the equation 1. So after we get this eigenvalue, right, we put this back in the equation 1, and from here we found the value of x. We basically found the solutions of this x, right? We basically found the solutions. So yeah, now this solution is different. This is the solution of the eigenvector itself. Here there was some other solution, right? There was some other solution. Okay, so yeah, basically we were finding this x itself. We were finding this x, right? We were finding this x. So yeah, we'll get eigenvectors which are basically column matrix only here in this case. Okay, so we'll get n eigenvectors. If there are n distinct eigenvalues, we'll get n eigenvectors. Or what is the relation, I will talk about that later. So eigenvector corresponding to lambda 1 will be this, eigenvector corresponding to lambda 2 will be this, right? So we'll get n eigenvectors. It depends. So each eigenvalue will correspond to its own eigenvector. Each eigenvalue will have its own eigenvector. So like, what are the terminologies? So I mentioned this E matrix, right? This E matrix has some name. This is the characteristics matrix. As this is also known as like eigen, right? Eigen means characteristics. That's why in German. So here it is known as characteristic matrix. So this is a matrix. That's why a matrix. Now P lambda is the basically the determinant of A minus lambda I. Basically the determinant of this characteristics matrix, which is known as the characteristics polynomial. Okay. Next, if I make P lambda equals to 0, this becomes equation. This becomes characteristics equation. Now, if the roots, what does the roots of P lambda say? These are the roots, right? Basically the values of lambda. What does the roots of P lambda say? Basically lambda means eigenvalue. First thing, lambda means characteristics roots. So this we have already understood from the characteristic equation from our control system chapter. If you have studied control system for me, you will know this. Next, it is also known as latent roots. So if in the question they ask to find the eigenvalue, we already know what we have to do. We have to make this determinant A minus lambda equal to 0. If they are asking to find the characteristics roots of the matrix, what does that mean? That means basically the same thing, eigenvalues. If they are asking us to find the latent roots of the matrix, that means also basically the same thing, eigenvalues. Okay, now let's study few shortcuts. Just hold on a second, everything is recording, I need to check. Let's study few shortcuts. So if I study few shortcuts, here our characteristics equation for 2 cross 2 matrix, lambda square minus trace of A into lambda plus determinant of A equals to 0. So this is basically the shortcut of characteristics equation for 2 cross 2 matrix. Why is this characteristic equation? This is by making this determinant equal to 0. This is a shortcut, right? I told you, right? I told you the significance when we are solving for the 2 cross 2 matrix in the previous example. There we saw that this trace of A was there and the determinant of A was here, and this was with a minus sign. So that's why we got this. Now our characteristics equation for 3 cross 3 matrix. What will be characteristic equation for 3 cross 3 matrix? It will simply lambda cube minus trace of A into lambda square. So the coefficient of lambda square will be trace of A. Then it will be summation of minors along diagonal. Whatever minors are there along the diagonal, it will be the summation of that. Basically, it will be equals to, if I expand this, this will be equals to M11 plus M22 plus M33, okay, into lambda. Now this is with a plus sign, this is minus plus, then I again write a minus sign with a determinant of A. So if I find the determinant of A, that will be the simple constant term over here, minus determinant of A. So plus lambda cube minus trace of A into lambda square plus summation of the minors, diagonal minors, minus determinant of A. Okay, these will be the this will be my characteristics equation. So basically let's do one example, and from there we'll understand whether this is true or not. Okay, whether the shortcut that I have written is true or not. So you have to remember these two. This one is easy to remember, and this one you have to remember, no other choice, because this is very important. This is very important, and this is very useful. And this one you can or you cannot, but I will suggest you remember this. During my preparation also I have remembered this. This is easier for us to remember. Trace of A and determinant of A is easy. Just the minor is a bit difficult. Okay, so basically let's now find the characteristic equation of the following matrix. This is a 3 cross 3 matrix. So what I will do, I will simply use the normal method at first, right? Normal method 1. Normal method. Okay, so if I use a normal method, what does this mean? This means A minus lambda I has to be, determinant of A minus lambda I has to be equal to 0. Lambda has to be equal to, that is the characteristic equation. So what is, like A is 2, I will subtract 2 minus lambda. basically subtracting along the diagonal elements. 3 minus lambda. Lambda e means only diagonal elements lambda is present. Everywhere else it's 0 only. So I am doing this quickly now. 4 minus lambda, and this is 3, this is 5, this is 4, 0, 0. This determinant equals to 0. And okay, fine. Okay, I'm just choosing one color. What color should I choose? This color is fine. Yeah, now we just compute the determinant, right? If you want to compute the determinant, this is basically bit easy to compute the determinant, because just I have to, this is a upper triangular matrix, so this will be the product of the diagonal elements. So this will be equals to 2 minus lambda, 3 minus lambda, and 4 minus lambda. Now in this case you might say, sir, now it becomes easier, right, to find the value of eigenvalues with this basic normal method, right? But like many times what will happen, finding the determinant will be difficult. That's why we use the shortcut method. But now obviously I chose a easy matrix, that's why you find it easier. So let me convert this into the characteristics equation. So if I convert this into the characteristic equation, this is 2 minus lambda into 3 minus 3, this is 12, plus lambda square, this is minus 7 lambda, equals to 0. Okay, now this is minus lambda. If I just multiply minus on both sides, right, this will become 0 only, and this will be lambda minus 2, because I want to keep my lambda cube positive. Coefficient of lambda cube is 1 positive. So this is lambda cube plus 12 lambda minus 7 lambda square minus 24 minus 2 lambda square, then plus 14 lambda, okay, equals to 0. So my lambda cube uh, 12 lambda plus this is lambda square, right? So this will be minus 9 minus 9 minus 9 lambda square plus 26 lambda, okay, then minus 24. Okay, so this is my characteristics equation. Now let's do this using the method 2. Okay, method 2, using the shortcut. So if I use the shortcut, what is the shortcut? Shortcut is basically this, right? I'll just copy and paste. So if I copy paste, so basically this will be lambda cube only. And what is the trace of a? Trace of a is 2 plus 3 plus 4, which is 5 plus 4, 9, and it will be minus 9 lambda square plus summation of minors along diagonal element. So how to add the minors along diagonal? So the diagonal element is this, and the minor for this diagonal element will be this 2 cross 2 matrix. This is 3 4 4. So this is 3 times 4 minus 0, which is 12. So this will be 12 plus. Now I will take the next diagonal element 3. If I take the next diagonal element, I will cancel the row and column. So this is 2 times 4 minus 0, which is 8. This is now this last diagonal element. If I cancel this one out, this is 2 cross 3 minus 0, which is 6. Okay, into lambda plus not plus, minus the determinant of A. Now what is the determinant of A? Okay, determinant of A is very simple, just a upper triangular matrix. 2 times 3 times 4 is 24, right? 24. So it will be minus 24. Okay, so pretty simple. So yeah, this is how you basically find this. So as you can observe, this is also much quicker. and when the determinant is pretty difficult to find out, right, you can use this because there will be lambda cube terms over here. Lambda cube, there is x. This is not just simplifying the determinant, you have to use lambda also. That is the difficult part. That's why you can use this method when like it becomes a bit lengthy with the normal fundamental method. Minus 9 lambda square plus 26 lambda and minus 24. This is ix like, oh no, this is not right, this is okay, minus 24. So this is basically the shortcut. So basically this is the end of this lecture. So in this lecture, what we learned about what is the eigenvector, what is the eigenvalue, the definition of eigenvector. Eigenvector basically scales the like scales itself. If I apply the eigenvector of a matrix, if it is multiplied with the matrix itself, simply it will be basically the scale version of that. It will be simply scale version of that. Lambda times this, right? What your definition? We learned about orthogonal. So here, right, it will be simply the scale version. If I multiply it with a matrix, it will be simply the scale version of it. It was later on here, I think. Where was it? Not even here. Where is it? Here, right? Scale version of it. Okay, so I hope you got the point, and also we learned about what are vectors. For now, just understand that vector are either row matrix or column matrix, okay, in a matrix definition. And what are eigenvalues? Basically the scalars which are multiplied by the eigenvectors after applying the transformation is known as the eigenvalues. Okay, we learned about orthogonal vectors, orthonormal vectors. We learned about linearly dependent vectors and linearly independent vectors. Linear dependent and independent are basically from the rank we can find out. Okay, and orthogonal vectors, we talked about the inner product. Okay, basically it is about the orthogonality of you can say in vector, right? Orthogonality vector we are representing it in matrix, because when we send data in the computer, right, we need to put it in the matrix format, not in our normal format, right? Computer can't understand our normal format. We have to make the data so that readable, so that our computers can understand, and we make the data readable by converting it into matrix format. So yeah, I hope you like this lecture, and in the next lecture we will start with the properties of eigenvalues and eigenvectors. Thank you for watching.